Hi guys, my name is Parapal and welcome back in my new video of design of 2-way slab numerical, in which I'm going to explain you the step-by-step numerical solution for your examinations, and you can prepare for your examination in very proper way, right? So this numerical is having the very different scenarios that will definitely give you good understanding of the design of 2-way slab. Before start this video, you can read this notes on my website www.civilnotes.com. Okay, and don't forget to visit this website because this website is very important for all civil engineers, right? So let's get started. Let's understand the numerical first of all. So the numerical is design a simply supported 2-way slab. We are going to design a simply supported 2-way slab over here over a room of 4.8 meter by 4 meter. Okay, it means we have a room of 4.8 meter. This is a distance of 4.8 and this is a distance of 4 meter. Okay, and it is effective first of all, right? Subjected to uniformly distributed load of 5 kilonewton per meter square, right, inclusive of self-weight. So this load does not consist any factored load. This is inclusive of the self-weight, right? Now we are going to use M20 grade of concrete and Fe 4 and 5 steel, right? So we need to draw a reinforcement detail check for shear also. Okay, may not be given, but we have some factors such as Ax equals to 0.084 and Ay equals to 0.059. So that's two things we have. Okay, so now let's calculate it step by step. So the given database is that we have the effective dimension for the 2-way slab is 4.8 meter by 4 meter. Load as a 5 kilonewton per meter square, which is the inclusive of the self-weight. Character strength of M20 grade of concrete, which is FCKVR, is become 20 Newton per mm square, and for Fe4 and 5 become 4 and 5 Newton per mm square. Now we have a coefficient of Ax and Ay as a 0.084 and 0.059 as a given in the numerical itself. So as you understand, whenever we are doing the design of the slab, we do require a modification factor, okay, and the design constraint. Okay, so here modification factor I am using as assuming as a 1.4, and as you understand, the limiting moment that we need required for the Fe4 and 5, okay, limiting moment that we do require is become 0.138 FCK into PD square. So we are going to put, or we are going to use the limiting moment to calculate the moment for this slab. So first of all, let's calculate the effective slab thickness. So the slab thickness formula is very simple guys, which is small t equals to whatever the span you have. So we have a span of how much? 4 meter. So 4 meter divided by 20 into modification factor. So I am converting all the data in the mm. So 4 meter become 4000 mm. 1.4 is a assume modification factor 20 as it is. So I got a effective depth as a 142.86 mm. So I am considering it as a 155 mm. Understood? Now let's assume that I'm going to use 10 mm main bar and clear cover of 20 mm dia. Now you should understand this figure, very important. This is very important situation. This is the first bar, this is the another bar, okay, and so we need to calculate capital D. So to calculate this, we have now effective depth. So we need to also add this database including clear cover. Sorry, this is clear cover. Okay, we need to add plus diameter of half of diameter of this bar, which is by divided by 2. So to calculate the capital D, so what is the effective depth? 150 mm plus clear cover I am assuming as a 20 mm plus 10 mm bar, you need to make it half of that, which is 10 by 2. So our total depth is 175 mm. Okay, now go to the next step, effective span. Now we have effective span, so I can say that this is my slab. Okay, so this is my L YE, this is my LXE, and I'm going to consider, okay, a 1 meter wide strip across the slab like this, which I'm going to design. Okay, so this is a 4 meter, this is 4.8 meter. So if you convert into mm, so it becomes 4800, it will become 4000 mm. Okay, so that's I have written here. Now let's consider 1 meter wide strip which we have considered. So we have a given load of 5 kilonewton per newton meter square. So 5 into 1 meter because 1 meter wide strip we have considered. So it is the total load is 5 kilonewton per meter square. But now make it a factor for future construction. So multiplied by 1.5, it becomes 7.5 kilonewton per meter. Now we have the next step is we have a factored bending moment calculation. For that we have some factors, alpha x and alpha y. So moment x along the d direction, okay, so that is ax into wd into l square x. Okay, so put all the value that you have here, you will get moment x into d is 10.08, and similarly for the myd you got 7.08 kilonewton into meter. Okay, now to calculate the effect, now this is what you calculate moment. Now once you calculate the moment, you need to calculate the effective depth of the slab. What is the effective required depth? Because here you can see this we have calculated based upon our data assumption. From that we calculate the capital D. Now we should understand what is the requirement. So to understand that requirement, we should use this formula of the limiting moment, which equals to the highest moment across these two value. Okay, so the 0.138 FCK is a 20, B is 1000 standard 1 meter wide strip we consider. This we need to calculate. 10.08 is a moment, this is in a meter, we are considering this is in a kilonewton, we are making multiply by 10 by 6 to make it in a newton. So the depth required become how much? 60.43, and what we have 150 mm. Hence your design is safe in terms of the effective depth. So whatever you have calculated, the depth that you are going to provide, which is 150 mm, the effective depth, that is more than what you should provide. So you are okay with that. So first of all, let's calculate the area and the spacing with respect to this database, right? So the area along the x direction is, this formula is very standard guys, you should know. It is 0.5 FCK upon Fy, 1 minus under root of 1 minus 4.6 m moment upon FCK into BD square into B into D. So here everything you need to put, every value you should have, M20, Fe4 and 5, this is 4 point standard, this moment that we calculate which is MUX, okay, 20 is a FCK, 1000 is a B because 1 meter strip, and this is 150 square, or you write 150 into 150. Similarly 1000 into 150, the same figure you need to write here. So you got an area as a 191.278 mm square. Now for this area, now this is the first area, understand, this is first area you calculated based upon what? The spacing you have, the effective depth you have. Now I'm just decided that for this I can provide the effective the bar of 8 mm dia and the spacing of minimum ABC from all these things 1, 2 and 3. So these are three formula. The first formula is yes, spacing equals to pi by 4 into diameter square multiplied by 1000 divided by AST. So you can see I have put it all the value. Okay, I got the spacing as a 260 mm center to center. Now the second formula is 3 into D. So 3 into what is the effective depth? 150. So it will become 450. Okay, and the third one is the maximum is a 300 mm. So among the three value, what is the minimum one? The minimum value is 260. So I am considering therefore spacing as x direction consider as a 260 mm center to center. Now from this you should again calculate the effective depth, because what happened is we have considered 8 mm bar and the above top we have considered how much? 10 mm bar. Okay, so here a conflict. So what I'm going to do is I'm just again going to calculate the effective depth, another effective depth. So how it is calculated? Whatever the effective depth you have considered, just need to minus the bar which you are going to select. So I'm going to select in the 8 mm bar, because this all calculation spacing I have calculated based upon the 8 mm bar, right? So 150 minus 8, it become 142. So you need to again calculate the area, okay, for which bar along the y direction. This is I am calculating for the y direction, okay. See, that's very simple thing. This is I am calculated for the x direction, okay, and this is I am calculating for the y direction, this one, okay. So my spacing for the both direction is changed. It doesn't mean that the spacing should be different for the different locations, right? So I'm putting every single thing, only thing will change what, that the movement for the y direction is will change, and the effective depth also change. Rest everything will be same as it is. So you got the area along the y direction as a 141.07. But now wait. Now see, AST along the x direction, AST along the y direction. So x direction I got as a 191.278 for 10 mm bar. Okay, and for y direction I got for 8 mm bar as a 141.07 mm square, right? But what is a minimum requirement? What should be the minimum requirement? That should be there itself. More than that you can assign, but not less than the minimum requirement. Otherwise your slab will fail. So the AST minimum formula is 12% of B into D. So 0.12 divided by 100 into 1000 is 1 meter, multiplied by capital D is 175. This is the overall depth. So your minimum AST is okay, is 210 mm square. So that 210 is more than both this figure. So this figure are not allowed at all. So you need to consider 210 mm square as the minimum still requirement. Since this ASTY is very low, so we are going to take ASTX and ASTY as a 210 mm square. So let's again calculate the spacing, which is similar for the both the direction. For 8 mm bar, which is Sx and Sy equals to pi by 4, 8 square into 1000 divided by AST. So pi by 4, okay, and AST will become 210. So you fill this value, you get 239. So I am considering 230 mm center to center, okay, which is less than this value 300. Okay, so this value should be less than the 3D and the minimum value, the maximum value 300. Okay, so I am considering 230 mm center to center with the 8 mm bar. Okay, so this is a graphical representation. Now understand the graphical representation. From here to here, this is your 4 meter. From here to here, it is your 4.8 meter. This is a one-sided bar. This is another sided bar. So you can see this is your top bar. Okay, this is your another bar, and this is the main bar, and these are the distributed bar. Okay, so this is a graphical representation that you have, okay, to perform the design of two-way slab. I hope you like this video. Okay, I hope you understand this numerical properly. You can use this numerical for your examinations. Okay, if you have any doubt, don't forget to visit my website www.civilnotes.com. This website is very crucial for all civil engineers. Okay, and this will give you lots of information related to civil engineering. Have a nice day. Bye bye.